Well, welcome back. This is the part two. We stopped at this point in last problem that we discussed, and I'd like to go over just the explanation why this worked and what's the relationship of this algorithm to this exactly what we did here. I want to show you that this algorithm is really doing this. Okay, that's what I want to show you as an explanation. And for this week, I will end it at that point, and I don't want to make it any longer for this week. And next week we will have probably longer lectures. Now, let me go through the explanation for this problem. I'm going to go to another page so we can see it. Explanation. Well, the digits that we discussed was 2F3A. I can say, well, this is a digit 0, digit 1, digit 2, digit 3, right? The example was 2F3A. We always look at the digits in this way, digit 0, because this one is to the power of 0. This multiplied by its base to the power of 0. This one is digit 1, or you can count them from the right to left by starting with number 0. And this is the least significant digit here, so D0, D1, D2, and D3. So let me explain why it worked. We wanted to calculate that value is equal to D3 times n to the power of 3, base to the power of 3, plus D2, right, times the base to the power of 2, plus D1 times n to the power of 1, plus D0 times n to the power of 0. This is what we said, right? It was 2 times, this is base 16, 16 to the power of 3 plus f times 16 to the power of 2 plus 3 times 16 to the power of 1 and plus 8 times 10 to the power of 0. This was our understanding of an anatomy of a number. So I can, instead of those digits, I put D3, D2, D1, D0, so generalizing. And why this algorithm works? Well, one thing that we could do, I know anything to the power of 0 is equal to 1, so this would be D3 to the power of n to the power of, this is basically 1, right? So this is D0. Here I have they all have this parameter n, so I factor out one n from these guys, and then we'll see what happens with that. So, and this would be D3 and 2 plus D2 and 1 plus D1 times n. I factor out n plus D0. And then I notice that here D1 doesn't have any n. I can factor out the n from here. So this would be the 2 parentheses D3 times n plus D2, right, times n plus D1 times n plus D0. And now what I could do, I could take this D3, replace D3 by, open up two parentheses, 0 times n plus d3, which is true, right? D3, if you replace them, you replace them 0 times n 0, what's left? D3. So D3 is equal to D3. So I replace D3 by this. Let's see what happens in this situation. Then this is equal to 2, 3, 4, because I have 2 here and 2 here, 4, 0 times n plus D3 times n plus D2, close another parenthesis, times n plus D1 and close parenthesis n plus D0. And isn't this exactly what we did? On the first pass, it evaluated what? On the first pass, it evaluated 0 times n, we said we start with digits, we pick the digits from the left most, 0 times n plus D3. That's exactly what we did here. You see that? Value was 0, 0 times n plus D3, 2. 0 times n plus D3. And the next time, we took the whole thing as a value, which was the value, multiplied them by the base, plus D2, which was 15. And then multiplied them by n, again, at the next digit, D1. Multiply them by n again, and add them the last digit, which was a here, right, which is d plus d0. But if you write them this way, if you code it this way, then, which would be this algorithm that I showed it to you, therefore you don't have to have a limit on the number of digits, and you don't have to have know the base. Before you solve the program, you have to also declare the n, variable n, and say, well, variable n, is it initialize them to an integer and say it is equal to whatever the base is. And that's why this problem worked clearly. I mean, this algorithm worked because it was based on this calculation. Sometimes in order to come up with a good algorithm to write the software program, you need to be able to manipulate the data so you can come up with better solutions. All right, in next class, I'm going to discuss the decimal to base n. That would be my next discussions. And then after that, I want to talk about some binary, octal, hexadecimal conversions, because for some of them, it's very easy. And then we're going to talk about more of the binary data and how we represent them within the computer. Within the computer, it's where you keep the numbers or the registers, all right, or memory cells, and how we keep them over there, how we represent them, because we don't have just the positive numbers, we also have negative numbers. How do we deal with that? And we also have then floating point numbers, but I'm not going to go into that in detail, but I will explain it to you. And then we will talk about some terminologies that we use in computer architecture that I like to discuss them, so we all are familiar. And then we will, after that, then I will discuss some parts of the computer and chapter 1, and then we move on to chapter 2. So next week, I'll probably finish up these discussions, and maybe if I get time, maybe I'll discuss chapter 1, and then after next week, then we move on to chapter 2, and then I will assign your first assignments. All right, you have a nice weekend, and look for your next week's lectures on Monday or Tuesday. I'm going to try to post them on Monday, but sometimes it doesn't happen, so it will be on Monday or Tuesday. Have a nice weekend.